decompose the volume budget for us of the future Arctic?
Okay, thank you, Paul. Yes, so I'm going to be talking about the volume budget of the Arctic sea ice in a coupled climate model. So first of all, I'll just say a few words about motivation for actually doing this work. As we all know, the Arctic sea ice has been declining for a number of decades, and we expect the decline to continue in the future. And there's a lot of interest in our ability or otherwise to predict the date at which the Arctic will first become ice-free, and also the extent to which we can predict the ice cover at the end of summer in any particular year. So in terms of how we do that, global coupled models are arguably the best prediction tool we've got to do that. But if we use those to project future ice decline, we get a big range of spread in the predictions due to all sorts of factors, including how the sea ice models are formulated, how the actual sea ice model itself is formulated, the processes are represented, how they're represented, but also lots of other things, including the forcing that's received by the atmosphere and the ocean models that are used, uncertainty in the future emission scenarios as well. And also something else that's received quite more attention recently, I think, which is good, is actually internal model variability. The fact that you can, from just one model, if you do many future projections with just one model, you can get a wide variety of ranges of projection, and also the internal model variability adds considerably to our uncertainty and when we can predict the date of a future ice-free Arctic. So if we want to compare models, I think it's becoming increasingly clear, but because of all these differences, we need to go beyond looking at just the ice extent and the ice volume alone, and we need to kind of look a bit more behind the scenes, as it were, and to what processes in the model are causing those changes, and are they the same in all models or not. Now in the future it's going to be much easier to do that when comparing different models, because for the next round of models that we'll have for the next IPCC assessment, there will hopefully be quite a comprehensive range of sea ice diagnostics available because of the work of the Sea Ice Model and Comparison Project and the diagnostics that have been requested by them, so that a number of different types of budget can be done: heat budgets, freshwater, momentum budgets. That's not to say that that sort of information hasn't been available from models in the past, but it's not been kind of collected together in previous model and comparison studies, and the new data will enable things to be done in a much more systematic way, and hopefully with diagnostics that are well defined, so that you know that you're looking at the same thing in two different models. But that's for the future. Here we're looking at just one model, so looking at the volume budget of a model from the last IPCC round, the AR5 round. So just to very briefly talk about the model itself, it's a Met Office Hadley Centre model. It's a global coupled model. It's an Earth system model, so it has some Earth system components, atmosphere and ocean carbon cycles, for example. The ocean and the ice are resolution, 1:1 resolution. The atmosphere model is slightly coarser resolution. The sea ice model is not actually SICE itself, but it is based on a number of the components of SICE. It has EVP ice dynamics, it has a ridging scheme, it has got subgrid scale ice thickness distribution. The thermodynamic scheme is 0 layers, so it doesn't have multi-layer ice, and the albedo is a function of surface temperature and snow cover. So just to talk about the projections that I'm using from this model. So actually, I don't know if you can read the anyway, so we're looking at the period from 1960 to the end of the 21st century. So from 1960 to 2005, the model was forced with historical emissions, and then from 2005 onwards for a range of forcing scenarios, which are illustrated in this plot. This plot shows the annual mean, global mean, near surface temperature, just to show what the projections are. And there's 4 different scenarios. There's the RCP 8.5 scenario in red, which is the most aggressive scenario, where there are ongoing increases of CO2 levels in the atmosphere right out to the end of the 21st century. And then the lowest emission scenario is the 2.6, where CO2 levels stabilise and actually start to decline by the end of the century. So in this model, the sort of global temperature responses you get range from over 5 degrees for RCP 8.5 and about 2 degrees for RCP 2.6. And then on the right, here is the response of the ice area and the ice volume to those forcing scenarios. So these are both averaged over this region up here. So the Arctic Ocean and the Kara and Barents Sea. So these, for both the ice area and the volume, this is for March and September. So the solid lines are March and the dashed lines are September. I think the main things to maybe note from this, well, the ice area and the volume are declining, of course. Before about 2060, there's not much divergence from the different forcing scenarios. After then, you do see a steeper decline in the area and the volume for the higher emission scenarios and the lower emission scenario, as you would expect. So for March, you do see divergence between the different forcing scenarios, but for September, you don't really, because by the time the scenarios start to diverge, I mean, there is a bit of divergence, but by the time they start to diverge substantially, there really isn't very much ice left in the Arctic, so there's not much difference to be seen there. So those are the runs. There's an ensemble of 4 members for each scenario and for the historical period. So now if I talk about the budget, the terms that can be we can decompose the budget into for this particular model. So this shows the seasonal cycle of ice growth and melt. This is a 20-year mean from 1960 to 1979, which we'll take as a reference period. So each component is expressed as the change that it expressed as an effective change on the, each component is expressed in terms of how it changes the mean ice thickness as if it were averaged over the whole domain of the Arctic. So this budget is constructed as a closed volume budget. So if you sum up all the terms, they balance the actual changes you're seeing in the ice volume itself. So the terms that are decomposing it into, I'll just talk about the main ones we'll look at. So the sum of all the terms is this black line here. So obviously we have melting. The blue line represents melting at the top surface of the ice. So obviously that occurs during the summer melt period, most notably during June and July. The light green line is melting at the base of the ice, so that's here. So again, there's some of that occurs all year, but obviously more during the summer melt period. And those are the two those two terms are then offset by the growth at the base of the ice during the winter, which is the dark green term. There are other terms plotted on here which I'm not going to talk about so much. The blue-green line is the ice loss due to ice being evicted out of the domain we're considering. The orange line is frazzle ice formation, and the red line is snow accumulation. Just to mention some terms that aren't on this plot. There's no lateral ice melt term here because this model doesn't explicitly have a lateral ice melt. There's no ridging because that's changing the distribution of the ice volume but not changing the volume. And there's no snow ice term because I'm considering here, which I didn't mention, that we're looking at the ice and snow together because we can't separate out the budget in this model for the ice and the snow. So those terms are not plotted here. So that's the mean seasonal cycle for 1960 to 1979. So then okay, so now I'm going to look at how that changes in the future. So this shows, so up here we see the same thing again, and then plotted on the same graph is the seasonal cycle for a decade, getting on to halfway through the 21st century, 2040 to 2049. And the big plot shows the difference between the two. So in terms of the volume budget, the closed budget, the times of year at which there are terms in the budget that are causing net ice loss occur at 2 times of year, May and September to November. So in May, we see more melting at the top surface of the ice here, due to this blue term, more melting at the base of the ice, and reduced basal ice formation. And then during September, October and November, what we see is a reduction in the basal ice formation term in the volume budget. And those terms are offset to some degree by what happens at other times of year, particularly in July and August, where overall we've got less melting at the top surface of the ice and less basal ice melt in the volume budget. Now, the reason that the volume budget looks like that is because this is a combination of what's happening to change the processes over the ice itself that remains, and the fact that the ice itself is actually declining, which is illustrated here. So what I've plotted here is 3 of the terms from the volume budget, but I've plotted them instead of how they contribute to the overall volume change itself. I've plotted the terms per unit surface area of the ice that is remaining, but of course the ice area is changing. So in terms of how the processes are changing over the ice, we see, we see big increases in melting at the base of the ice. So for the ice that's there, there's a lot more melting at the base of the ice, as we'd expect, particularly towards the end of the summer. You see more melting at the top of the ice. In our model, that only occurs earlier in the melt season, and it doesn't tend to occur later in the melt season. That's probably partly to do with the way that we parameterize albedo in the model. In our control run, by July, the surface temperature of the ice in the control integration is at the melting temperature, and the albedo won't be able to change any further. And then we see here, we see that in the winter, for the ice that's there is more basal ice formation over the ice that's there because the ice is thinner. But it's actually the combination of what's happening over the ice itself and the fact that the ice area is changing that leads to this this change in the volume budget. So it's kind of 2 different ways of looking at the changes, and I think what I'm saying really is that there are 2 different things to look at. How are the processes changing at the ice itself, and what's the impact of those processes on the volume budget due to the fact that the ice is actually shrinking. And because the ice area declines more quickly in September, August and September, and in the autumn than it does at other times of year, processes at the ice that change a lot then can have a more perhaps unexpected impact in the actual volume budget. So those changes I've talked about were all for the RCP 8.5 scenario. So now I just want to have a look at what's the actual impact of the forcing scenario on these changes. So what I've plotted here is just one of the terms, which is the growth at the base of the ice, and how the sort of evolution of that with time. So going out from 1960 to 2100. So this is the run that this is the RCP 8.5 integration. So what we see is that for the we see the sort of ongoing decline in the amount of this because of the declining ice area. So for the other scenarios, we see a broadly similar signal of how things are evolving, but the exact timing and magnitude of the change depends, as I think we probably expect, on the strength of the forcing scenario. And we see much the same thing for each of the budget components, which I won't show there, but perhaps more interesting is to look at how each of the components changes, not as a function of time, but as a function of the evolving ice area. So here I've plotted each component separately. So here we've got all the scenarios on the same plots. We've got ice area, and it's going from the the beginning of the run here with the largest ice area down to declining ice area here. And also just to note that these plots all have very different scales. So the point here isn't so much to compare the relative importance of the different terms, but it's to show that in each case the term follows a common trajectory for all the different scenarios. So what that's saying is that within the volume budget, the amount by which the terms are changing depends on the ice area, and it doesn't depend on how quickly the ice got to that state. So if it got there very quickly in the RCP 8.5 scenario, or if it got there in a much more leisurely way with the RCP 2.6 scenario, in this model we still would get the same balance of terms in the volume budget and that's the case for this model, and it's the case for the range of forcing scenarios that we've considered. I suppose the other thing to say is obviously these trajectories are not all linear. Some of the terms change sign. Someone looks if there's a change in slope. This is plotted against decadal mean ice area. If you plot against September ice area, the points at which you tend to see a change in sign or a change in slope corresponds to roughly when the Arctic starts to become ice-free at the end of the summer. And the reason that you get a change in sign, so for example for the basal ice melt, what happens early on is that you're getting early on, the dominating factor is what's happening in the beginning of the melt season, and the dominating factor is the process that's occurring over the ice, the extra melting. But by the end of the run, what's dominating is the fact that you're just getting less melt at the end of towards the end of the summer, because there just isn't very much ice there anymore. So you've got more impact of the ice area here, and you've got more impact of the actual process changes over the ice here. If that makes sense. Anyway, that's, I think, probably all I'm going to say. So we've looked at components of the Arctic sea ice budget in one model, Hadgem 2ES, and how that changed over the 21st century. So as the climate warms, over the ice that remains, we see that there's extra melting at the top surface early in the melt season. There's extra melting at the base of the ice due to heat from the ocean during late summer and autumn. And then there are smaller increases in basal growth during the winter due to the thinner ice. But if you want to actually use those changes to balance the ice volume changes, the declining ice area has to be taken into account. And then the biggest changes that you see in the volume budget are a net ice loss due to reduction in the total amount of basal ice growth, and that's partially offset by reduced amounts of surface and basal, reduced total amounts of surface and basal melting, and also, which I haven't really spoken to about particularly, reduced loss of ice by advection to lower latitudes. And also for this model and for the range of scenarios that we use for AR5, the change in the volume budget components depends on the ice area, but not on the speed at which the ice area declines. Thank you.
Thanks, Anne. Very nice. Any questions, Brad?
Yeah. Do you have rapid decline in your model?
Sorry.
Do you have rapid sea ice decline in your model simulation?
In this one, yeah, it's fairly rapid. It's not, yeah.
What are they caused by?
Sorry?
Sorry. I'm just wondering if you have rapid sea ice decline and what they're caused by.
If we have rapid sea ice decline, it's in the main model pack. I mean, it's not faster than observed. Right? Yeah.
Okay, maybe one just a clarification. You said that you don't have the lateral ice ablation in your model.
Don't have what? Sorry.
Lateral ice ablation.
It's not explicitly modelled as a separate.
The warm water can reduce the ice extent.
Yes.
By flowing into it, right?
But it's not. There's no explicit parameterisation of that separately from anything else. Yeah, which is why it doesn't appear. Yeah.
Okay, we should move on. So next speaker is Jamie Ray, again from the Met Office.